Welcome to the pre-class video assignment for section 2.8. So in this section, we're going to look at solving higher order linear differential equations. So up until now, we spent some time with first order, and then we spent some time solving second order. We're going to take a little look at higher order. The good news is that higher order equations, the differential equations theory behind it all is basically the same thing. So we don't need a whole lot of new ideas here, if any, from differential equations anyway. The bad news is that, of course, the execution of these methods and the algebra in these methods becomes a little trickier. So we're going to review a little bit of the algebra that we're going to need here. But again, basically, an nth order differential equation would look something like this, with an nth order derivative in it. It's going to have, again, a g of x on the end. If g of x is 0, it is homogeneous. If g of x is not 0, it is non-homogeneous. We're going to look at both cases in this section, but we're going to start with homogeneous. We will also look at you will see solve some initial value problems, mainly in the exercises, but an nth order initial value problem is going to have n conditions on the y prime, the y double prime, all the way to the y, the sort of n minus 1th derivative of y will have a condition. So those would be where we have our conditions for our initial value problem. But again, mathematically, it works very similarly to before. We are going to start off with looking at the homogeneous case equals 0. What we learned about this for the second order case was that we basically need to write the characteristic equation for this dE, which would look something like this, again, fairly easy. And we need to solve the characteristic equation and find the roots of the characteristic equation. And it's the roots of the characteristic equation that basically dictate the nature of the particular solutions, the set of linearly independent solutions. So we call this a fundamental set of solutions. And this is basically dictated by these roots of a characteristic equation. The good news is, for third, fourth order DEs, the exact same theory applies. What you actually end up doing with the roots of your characteristic equation are exactly the same, but it's just a little bit harder to solve the characteristic equation. The algebra for solving cubic equations and higher degree polynomial equations is tricky. There is no practical cubic equation, no practical quartic equation that we can rely on to solve any old higher degree polynomial equation. So we have to sort of resort to a bit of a bag of tricks here to try and solve at least some of them. So we're not able to solve any old cubic or quartic, practically speaking, but we can solve a lot of them by some of these methods. So this is what we're going to look at. How do we solve higher degree polynomial equations? So we're going to review the algebra of this first before we talk about the differential equations of it. So this is usually the strategy I would suggest. Can we factor? Sometimes guessing, if you can come up with one particular root or one particular solution, you can use it to find other particular solutions. So that's a possibility. And there is something called the rational zeros theorem, which is also helpful to at least get started and find a one starting root. So let's take a look at the algebra of this situation. So again, as mentioned, as a general concept, solving higher order DEs requires solving a characteristic equation. Homogeneous, we're talking about homogeneous here. Yes, for degree order 2 differential equations, the characteristic equation was always quadratic. And again, this is something we can always solve. We can always determine the roots, whether they are real or whether they are complex. And we determined what the solutions would look like, no matter what kind of roots we had. So that was good, right? So how does this work then theoretically for higher degree. So these are sort of some of the tricks that we can try. Number one is, can we solve by factoring? So just because it's not quadratic doesn't mean it doesn't factor. A lot of them don't factor, but they might have some that factor. So for example, is there a greatest common factor that you can factor out and get started with? Factoring by grouping was a trick they usually used for factoring cubic equations. And then another possibility is having something that is quadratic in x to the n. So x to the 4 minus x squared plus 7 would be quadratic in x squared. So if you recognize it as such, you can solve it by quadratic methods, solve for x squared by quadratic methods. So again, factoring we should be aware of. We should be able to factor, so we will see that a little bit, but also I'll leave that for you. The other option here is finding a starting zero. The idea here is if you can find 1 0 from a polynomial equation you're trying to solve, you can divide it out and reduce the degree of the polynomial that you're trying to solve. So finding a starting zero is quite helpful. Usually this would then involve polynomial long division. So here's just a little example, just for argument's sake. So for example, what are find the zeros of the following polynomial: x cubed minus 2x squared plus 3x minus 6. What are the zeros here? So here, let's suppose that we know that x equals 2 is 1. So x equals 2 is one of the zeros. So what are the other zeros? First of all, you probably should know from algebra, if this is a cubic equation, degree 3 polynomial equation, then it has 3 roots if you count them all. So if you count integer roots, rational roots, repeated roots, complex roots, if you count all the possible roots, there will be 3 of them in a degree 3. In a degree 5, there will be 5 of them, and so on. So I've been given 1 root, so I know there are 2 more to find. So the idea here is as follows, that if x equals 2 is a 0, then x minus 2 is a factor of this polynomial. These two facts go hand in hand. If x equals 2 is a 0, then x minus 2 is a factor, and then we can do polynomial long division to divide it out and see what else we have. So polynomial long division would look something like this. I'm going to take my x minus 2 factor, and I'm going to divide it into x cubed minus 2x squared plus 3x minus 6. Again, so remember how this works. In polynomial long division, you concentrate on the leading terms. So we basically ask ourselves, how does x divide into x cubed? X goes into x cubed x squared times, and then you multiply back around. X squared times x is x cubed. X squared times minus 2x is minus 2x squared. So we multiply back around, and then we subtract top minus bottom. So here we're kind of lucky. Those cancel, those cancel. The first term has to cancel. We got lucky in a sense, and the second term canceled as well. And then we bring down whatever is remaining, 3x and minus 6, and then we try again. How does x divide into 3x? It goes in 3 times. Multiply back around, and we get 3x. 3 times minus 2 is minus 6. We subtract again, and then we get 0. So you probably remember that this is your remainder, yes? So the fact that we did our long division and got a remainder of 0 says that x minus 2 divides evenly into our original polynomial. That is what has to be the case. If x equals 2 is a 0 and x minus 2 therefore is a factor, then when you do this long division, you have to end up with a 0 remainder. And then what we know is the following, that our original polynomial is equal to, we know there's an x minus 2 factor, and now we know that the rest of it is an x squared minus 3, x squared plus 3, excuse me. So this is the answer to our division problem. Again, check this out, foil it back out again, and you can see that this indeed is correct. This, if you foil it out, gives you this back again. So now we are good. We can now look for our other roots. So we can look for the roots in x squared plus 3. X squared plus 3, if you set it equal to 0 and solve, we find the roots. This is x squared equals -3. So these are complex roots, yes. This will be x equals plus or minus the square root of -3. This is plus or minus root 3i. So these are our roots. X equals 2 is a root, and then x equals plus root 3i and x minus root 3i must be the other roots. So this is actually a little fact we saw earlier in the course as well. The complex roots have to occur in conjugate pairs. So plus root 3i and minus root 3i are a pair of roots. And that must be all of them. There can only be 3 roots. We found all 3. So this is the idea. All right, so you should practice a little bit with this long division of polynomials. So there's a couple of examples here to try. And then there's a second one to try just for practice. All right, then. So in that last example, we were given a root, right? We were given a starting root, and that got us started. In general, of course, that's artificial. You don't necessarily, no one's there handing out roots to you necessarily. So how might we find a root? So a couple of things we can do. This is sort of cheating. It says finding a root by inspection. That means just try some easy roots and see if you get lucky. Is 1 a root? Is -1 a root? And again, the point would be is that if you put in 1 into the function and you get out 0, then 1 must be a root, and so on and so on. Another option, kind of another cheating option, is graph the polynomial expression as a function on your calculator. And again, the roots will be x-intercepts. So you might be able to spot integer roots, so guess them from a graph. So that is another possibility. But a slightly more formal procedure for finding a root is something called the rational zeros theorem. So in the rational zeros theorem, it says the following, that basically, if you have a polynomial with integer coefficients, then rational zeros will have the form p over q, where p is any integer factor of the constant term on the lead constant term, p is any factor of the constant term on the end of the polynomial, and q is any integer factor of the leading coefficient of the polynomial. So a little example, let's use that same example again. If I were to look at x cubed minus 2x squared plus 3x minus 6, and I want to ask myself, what are the possible rational zeros here? They would be as follows. So we would note that the leading coefficient is 1, the term on the end is 6. So this is what I usually do to write this out. I would say, here are my possible p-values. The p-values are all possible integer factors of the 6 on the end, plus or minus. So it doesn't really matter if this is -6 or +6. I include all possible integer factors of the number 6. Those are plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. The possible q values then are all integer factors of the lead, which is just a 1. So the only possible q's are plus and minus 1. And therefore, the possible p over q's, the only possible p over q's will be, so you just form all possible ratios of this. This is, again, not that difficult in this case. This is 1 over 1 plus or minus 2 over plus or minus 1 is plus or minus 2. 3 over 1 is 3. And 6 over 1 is 6. So this one's a fairly easy one, given that there are only only one possibility here. If there was another possibility here, you would form all those ratios as well. And these are a list, a finite list of possible zeros. And then all you have to do is check them all to look for zeros. Again, the convenient thing to do is to use your calculator feature on your calculator table feature. Put this guy into Y1 on your calculator and go to your table feature and start plugging in +1, -1, +2, -2, +3, -3, and so on. And again, if there is a rational zero, it has to show up in this list. And as we can see that here, this was our given. Remember, in this particular one, we were given +2 was a zero. Yes, we knew this. We were given this. Notice that it does indeed appear in this list. And 2 was the only rational zero. So none of these other values were actually ended up being zeros. So this is another more formal technique for coming up with a starting zero, the rational zeros theorem. Okay, so let's see how we can apply this to higher order differential equations. Let's look at some examples here. All right, so here is a third order homogeneous differential equation. Again, the theory is the same. We look at its characteristic equation, which would look like this. And again, we would start thinking about our methods here. So again, I usually start with at least quickly take a look and see if we can factor it. This one does factor. Notice the lack of a y term in the dE. That means there's a common m here. I can factor out the m, and I'm left then with a quadratic. If I am left with this quadratic, then that I can just factor, and this factors into x minus 4 times x minus 4. So I have the root m equals 0, and I have a repeated root m equals 4. So all I need to do at that point is, well, here's a little this means we have a fundamental solution set, of solutions to be what? So if m equals 0, our fundamental set of solutions will be a constant. So a constant, and then we have a repeated root. So this is, let's call that C1. Then there would be a C2 e to the 4t and a C3 t e to the 4t. This would sort of be our fundamental set of solutions. And again, we don't have to put them in with constants there. These would be, I guess we would just call these, just call that a 1. That shouldn't be with constants there in general. This would just be a 1, e to the 4t and a t e to the 4t. And then from that, we can form a general solution by a linear combination of them. Again, so that one was by factoring. The next one, it's a fairly typical question. The next one is, here is a, again, third order differential equation, easy to write into its characteristic equation, and we are given that m equals -3 is a root. So if m equals -3 is a root, then m plus 3 is its factor. So m plus 3 must be a factor to this characteristic polynomial. So if we do long division to divide it out, again, follow this long division problem. This one's pretty straightforward. I got a remainder of 0, which is always a positive. It means so far so good. If this does not come out to be 0, it means that this is a lie. Yes, this has to come out to be 0. So if that comes out to be 0, then we know that this is the rest of the polynomial. Our polynomial factors into m plus 3 times m squared plus 2m plus 4. So that's what we get. Again, we knew m equals -3 was given. The other does not factor as a quadratic, so you can do the quadratic formula, and I got this. So m equals -1 plus root 3i, and m equals -1 minus root 3i. So remember what we do with these complex roots. These are, so m equals -3 would give us this function, e to the minus 3t, and then these are the alpha is -1, the beta is √3, so we have a e to the minus t cosine √3, e to the minus t sine √t, form a linear combination of them is the general solution. The fundamental set of solutions is e to the minus 3t, e to the minus t cosine √3t, cosine √3t, and e to the minus t sine √3t. So again, here's one we've solved given a root. So try a couple of these then. Try one of these where the roots are given. This on my open math, this one's fairly easy. And then last but not least, this is a bit more work, but here is a fourth order differential equation. Again, they might not say this in every question, but this is probably your way to get started here is the rational zeros theorem. So if you form a characteristic equation like this, we need to find the roots of this guy. And again, unless we're going to guess it, rational zeros theorem ought to give us a place to start. So we do the rational zeros process, which is we look at the possible p-values. The possible p-values are the factors of 45, plus or minus. So those are plus or minus 1, plus or minus 3, plus or minus 5, plus or minus 15, plus or minus 45. And then the possible factors of 2 are plus or minus 1, plus or minus 2. And then you form all, so the possible rational zeros, p over q's, possible p over q's are 1 over 1 is 1, 3 over 1 is 3, 5 over 1, 15 over 1, 45 over 1. That gives us those. And then we also have 1 over 2 is a half, 3 over 2 is 3 halves, 5 over 2, 15 over 2, 45 over 2, and they are all plus or minus. So there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, plus or minus. There are 20 candidates for a starting root here. But again, it seems tedious, but it's really not that bad. The idea would be to go ahead and slap this onto your calculator into Y1 and go to your table feature and start plugging these guys in. Plug in a 1, a 3, a 5, and you're looking for, again, when you evaluate at any of these plus or minus, if you end up with an output of 0, it means you found a rational root. So I did this and I found these. That -5 was a rational root. So if you put -5 into this polynomial, you do indeed get 0. If you put 3 over 2 into this polynomial, you do indeed get 0. So there are 2. I actually went through the whole list and I found 2 of them. So that tells us that x minus 5 and x minus 3 over 2 are factors. A little bit more conveniently is that x equals 3 over 2 is a root for 2x minus 3. That's probably a bit more practical here. So those are 2 of our factors. If I multiply them together, I get a quadratic factor here that I know should be a factor of our original polynomial. So that's what I'm going to do next. Oops, excuse me. I'm going to take this guy here and I'm going to divide 2x squared plus 7x minus 15 into it by long division. Again, be a little bit careful here. This is actually fairly straightforward. Follow the long division. 2m squared into 2m to the 4 goes m squared times and so on. Again, I completed this. I got a remainder of 0, so that makes me feel like I did it correctly. Here is the quotient. This is the answer to the division problem, which tells us that our characteristic equation, this guy right here, actually factors like this. Again, we already knew the m plus 5, the 2m minus 3. This is the rest of it. It is an m squared plus 3. And so now we're in business. We have a fundamental set of solutions. They would be, I have root was -5. So there's an e to the minus 5t. There is a 3 over 2. So an e to the 3 over 2t. And then we have a plus and minus root 3. So that is in this case here, this is a 0 plus or minus root 3i. That is my alpha, that is my beta. So this means we have a cosine root 3t and a sine root 3t. This would be our fundamental set of solutions, and we can form a general solution by making a linear combination of them. So that is basically what we are after. So here's a little example for you to try. Try doing it using the rational zeros theorem. All right, that will be it then for this video. We will complete the rest of this together in class.